o'clock, and we welcome viewers to this digital investor meeting where we are joined by Freemelt. If you viewers have any questions during this broadcast, you may ask them in the chat below and they will be addressed during the Q&A. But without further ado, it is time to introduce our speaker, and I turn now to CEO Daniel Gidlund. Welcome.
Thank you. So good afternoon, everyone, and thank you for joining us today. With us today, we also have our CFO Martin Granlund and Head of Energy Per Boxenius, and I'm especially pleased to welcome Göran Backlund from Saab as well. We have a lot of interesting material to share, so let's get into it. So let me start with the headlines. If we look into our last 12-month revenue, it's up 162% year over year, if you take from end of March this year. We now have 42 machines deployed, but I think more important story is what's happening across our 4 verticals. In defense, we secured a follow-on order from a leading Swedish defense customer. We have also successfully wrapped up the copper project with Saab, Vinnova and Linköping University, where phase 2 is being discussed. In fusion, our fusion for energy tungsten tile work is progressing well, and we also received a follow-on order from UKAEA as well. Regarding machine sales, we have booked 2 new Freemelt 1 orders so far, which is series in Belgium and printed in Sweden. In medtech, we have 2 orthopedic OEMs running proof of concepts on our industrial machine eMELT. And here we also had a successful upgrade of the machine at one of the clients. So I would say real progress across the board. I want to spend a moment on where Freemelt now is in its journey, because we are entering a new chapter, and I think personally, I think this is the most exciting one yet for Freemelt as well. If we take a step back, chapter 1 started back in 2017. Then we built an open source platform optimized for research, which was the Freemelt 1 machine. And we used those years to prove that our technology could handle extreme materials like tungsten, for instance, but also copper, titanium as well, which are core focus areas. On top of this, and I think this has been the, let's say, the DNA from the start from Freemelt, is also to collaborate with our customers that have purchased our machines. And they have also at least validated more than 35 materials as well on top of this. Chapter 2 did begin in 2024, and that was related to when we launched our industrial machine eMELT. And then we moved, so to say, from the lab into more co-development with the industry. Saab is one of them that I mentioned before. I mean, the leading orthopedic manufacturers, also Fusion for Energy, we have UKAEA, we have Geely, IHI, and also several undisclosed industrial collaborations. And I would say since 2024, we have been managing a bit more than 30 paid customer projects, and all these projects are related to some sort of interest or intention of serial producing of new type of applications. And now, as I said, we're entering a new chapter, chapter 3. And this is the chapter where we as a company shall scale. And now we're combining our 3D printing machines also with finishing, machining, quality control. So we actually can deliver the finished certified parts straight into our customers' assembly lines. This means it's the same playbook, but a much bigger market. And we estimate somewhere between 41 and 51 billion euros in total accessible market. So where will the next orders actually come from during chapter 3? we have three demand pools which are converging on our technology. And it starts with medtech. So I'll start with medtech, and then Per will continue on the other two. So medtech, as I mentioned before, we work with two top orthopedic OEMs, and they are running proof of concepts on our industrial machine eMELT. On top of the proof of concepts, these clients also, as this is a regulatory industry, they must go through a certification phase as well, which typically takes another 12-18 months. And the good part is that, you know, when you really pass the certification, then you really also get in long term as well, because when it's regulatory, you don't really want to change the technology. So medtech is the industry that with the highest adoption of serial production of AM, and they are expecting also to have a CAGR of 16% until 2032, reaching 5.7 billion euro. So with that said, Per, I hand over to you.
Okay, again, my name is Per Voxenius. I'm head of energy and work primarily with fusion power. I'm going to tell you what we do, but before that, I want to say why we do it and why does the customers want our technology. First is that the material quality, that we can do parts of a quality, material quality in tungsten that has not been possible before. When it comes to density, when it comes to control of microstructure, etc. So that is what the material scientists love at Fusion for Energy. We can do parts with a longer life, because if we make parts with more complex shapes, we can design them for a longer life, and that is what the engineers like at Fusion for Energy. Resilience has become much more important, both in defense but also in energy. And the director at Fusion for Energy, that is sort of the main point for him when he wants to use our technology. And finally, all of this is only of interest if this is cost competitive, and it is compared to traditional methods. ITER is the world's largest research project in the world. It's about a 30 billion euro project. Europe stands for 40% of this, and it's Fusion for Energy that leads this. And one example of this is what is called the first wall panels. In total, there are 440 panels, which will be sort of the inside of ITER, covering 800 square meters. And 60 of those has already been ordered. So there are 60 panels already in production. It's an order of about, in total, 200 million euros, which two different companies share. And what happened in about 2 years back is that they switched from a material called beryllium to tungsten. So now they will put tungsten tiles on all of these. And this is about 185,000 tiles that needs to be placed on these panels. And now we have issue with China. It's not certain that China can deliver, or the opposite. It's probably that they cannot deliver tiles. They need someone else doing it. And we are one of the possible options. And 185,000 tiles, that would be around probably about 20 million euros if this translates. On top of that, there are at least 45 private companies working on this. In Europe, we have Proxima Fusion, we have Focus Energy, and quite a bit more. And we are in talks with many of them. And all of them look at ITER and see what they do and see which technology is used, and plan to use similar technologies. And what is the status now? We are currently qualifying tungsten together with Fusion for Energy. They investigate the material quality, but also joining technologies between this and heat exchangers. And when it comes to UKA, the United Kingdom Atomic Energy Authority, we have had one more order coming in, and that is a follow-up order on material science. So we work closely with them as well. We shouldn't forget big science, because there are a lot of connections between fusion, which is the big science technology, and other experiments. This morning I was in meetings with CERN. They are looking into new science experiments coming up further. We also, of course, are in discussion with ESS and other accelerators. And the benefit with this technology, what is needed in big science, they have the same requirements as fusion. So we don't have to sort of invent again or reinvent the wheel. We can just piggyback on what's happening in fusion. And again, these are also quite costly experiments, and in the next 10 years in Europe alone, about 32 to 42 billion euros will be used for expanding these facilities. And again, we are working on different tendering processes for different accelerators at the moment.
Excellent. Thank you, Per. So let me just make a quick introduction and an update also regarding defense, and then I'll let Göran introduce you more specifically to Saab. So the reason additive manufacturing matter in defense comes down to a few things. First, supply resilience. Countries these days want to print critical parts at home. Speed, additive manufacturing can make, you go from CAD to flight test in weeks. Cost, roughly for some applications like in missile components, 1/10 of the legacy component at scale. And also, I think, unfortunately maybe to say, but if you look into replenishment, the global conflicts are depleting stockpiles faster than traditional supply chains can keep up. And if you look into our technology, it fits in components where conventional methods and other, let's say, AM methods fall short as well. And typically, this is like hypersonic missile parts that can, survive extreme heat. They can be complex munitions and also propulsion components. So with that said, I'd like to hand over to Göran from Saab, who will take you through a deep dive regarding the additive manufacturing within Saab. So please, Göran.
Thank you, Daniel. I'm chairing the Saab AM board. We have a collaborative effort on additive manufacturing for Saab. So we can take the next one here. And this is Saab. Just a glimpse of the different areas that we operate in, from jet fighters with aeronautics, underwater systems like submarines, but also surface vessels. We have command and control and sensors, that is radar systems for air, land, and sea. And to the left, you have advanced weapon systems, and I'm representing advanced weapon systems. But since additive is a relevant technology for all these different business areas within Saab, our management team decided many years ago now to let us collaborate on this area, because these different business areas are very independent and we don't usually collaborate that much. But on a technology basis, there is a good reason to do so, so we don't duplicate work. So we can take the next slide. And we have very good management support for additive. And this is Michael Johansson, the Saab Group CEO. And he says, to remain relevant, each and every one of us must stay curious and embrace new technology. Now that we need to increase volumes, AM is a strategic technology that Saab is truly committed to. And that's true, because this slide is taken from a video, and it's an internal campaign that we have been running for about a year now that we call AM First, which is the call for the organization to really consider AM first as a means of production. We can move on. The Saab AM group, to the left, you can see we have representatives from all the different parts of Saab that I just mentioned. And we meet on a regular basis. And what we do, you see to the right, we have derived the Saab AM strategy. We're currently running the Saab AM First campaign. We have also developed what additive means to our way of working. So we have now an AM handbook for people to use. This is how you go about additive. And if you click once, you can see we have also derived a Saab AM learning path, a training package for our engineers. Available on our intranet. We have also together, which is pretty uncommon, run projects to together qualify materials, AM materials. So we now have about 3 different alloys available to our designers. They don't have to worry about the material properties. They have been proven, so they're ready to use. We also work on a common Saab-approved AM supplier list. We don't produce the components ourselves. We rely on our supply chain. And as Daniel pointed out, the security of supply is pretty important these days. To the right, you have upper right a picture from the annual Saab AM Day that we run digitally once a year to spread knowledge within the Saab group on what happens on additive. And we usually have 500 to 700 attendees during that day. And the way we do this now, we keep each other informed between the different business areas. We all know what the colleague in the other business area is doing, and we try as much as possible to find the Saab common solutions and work together. Can take the next one. Now, I'll just show just a few AM applications coming from these different parts of Saab. So we can take the first one. And this is now 12 years ago. And what you see in front of you is the Carl Gustav anti-tank weapon on a test stand during the qualification tests 12 years ago. And this is a titanium weapon, a lightweight titanium weapon to be fired from a shoulder and against a tank or some other target. To the left, you can see the breech or the Venturi. It's a recoilless rifle, so the Venturi sustains a lot of mechanical pressure, thermal load, and gas flow, supersonic gas flow. So we chose that part as a test article to prove to colleagues that additive is good as any other metal. So to the right, you can see the breech. It was printed in with electron beam melting, and it was put on the test stand, and we fired 3 first rounds, and that performed just as well as any other of the breeches, even though some colleagues didn't believe that the breech could take the load, but it did. So what we proved was that printed titanium is just as good as any other titanium. Next. This is another titanium part printed with EBM. That's a missile rudder. You can see the missile to the right, and in the little red ring, you can see the rudder. And it's about 10 to 12 centimeters big. And the challenge here is actually production. Today it's milled, and it's pretty hard to mill because it's so thin. But we proved here that you can print it just as well, and you can put a lot of rudders on one plate and produce a lot of them. You see a little pin on the top of the fin. It's not part of the fin, and that is only for post-processing, so you can fixate the rudder after it's printed in a milling machine and finish the part, and then it's taken off, so it's not part of the rudder itself. It's just for a fixture. Next one. This is actually the first component that went into serial production, and it's a cool plate in part of an airborne cooling system. To the upper left, you see the cool plate. It's 4 millimeters thick, but it's hollow. And high power electronics sits on both sides of this cool plate. And the coolant runs, you see the inlets and exit with the red plugs, runs in the plate, picks up the heat, and the complexity actually sits inside this plate. And we have used additive to boost the heat transfer of this plate. So you can see some of the results at the bottom. It's now printed as one part. It was originally intended to be assembled from several different parts. Since it's one part, it's leak-proof. We reduced the weight of the cooling circuit by 50%, and that includes the flow distributor to the right, where you put 4 of these different coolant plates. You see the assembly to the far right. People also started to innovate using additive because of the greater design envelope, and that rendered 1 patent. And this is in serial production, and it's an airborne system, so it's being qualified for its use. Next one. Here you have our anti-ship missile, Robot 15. We did a part screening some years ago to find which parts could we print that is a good business case for the product. And we started with a low criticality component like the front cover skin. It's on the leading edge of each wing on the missile. You have 4 wings per missile. And under the missile, you can see to the left, the original design. It was 2 stamped parts that were manually welded together and a riveted bottom on that. Now, we employed a topology optimization and fused all these parts and made it as one part now printed, where we save cost, lead time, and weight, and part reduction. So it was a pretty good case to start with, especially since it's a low criticality. And I think we have another case on the same product. Next one. Yeah, this is my last example. This is the air intake to the same missile, but the next generation Mark IV Robot 15 under development. And you see the air intake there to the gas turbine that sits at the end of the missile. It was originally designed for carbon fiber, to be produced in carbon fiber. But we had some challenges there, so we had to look at other alternatives. And it's now a very thin double-walled titanium solution inlet there. I think if we click once more, we can see some figures. Yeah. We reduced the cost substantially for this one, and lead time, and even weight, even though that original part was carbon fiber, and we reduced the number of parts. And the last 2 I've shown you now, the air intake and the front cover skin for the Robot 15, they are in the phase of actually going into production right now as we speak. So that's intended to be a production. And I just want to conclude to say what I showed you is what I'm at liberty to show you. The absolutely coolest cases I cannot talk about, but it's sometimes it's pretty breathtaking what we can do with additive when we get around to be innovative about it. So I see a lot of promise for the future with additive for Saab. Thank you very much.
Thank you, Göran. I think it's really impressive. I know let's say how much you've been fighting for this and leading this as well, and just the fact to establish also a culture in the organization in regards to new technology. I think that's a really big step. So it's really well done. So as I mentioned before, I mean, chapter 3 has started now for Freemelt, and one of the first and key components of this chapter as well is also then the warrant now, where the subscription actually starts today. So with that said, Martin, can you please share some further insights about this as well?
Absolutely. Thank you, Daniel. So the warrant is a tail financing from the share issue, which was done in the first quarter of 2025. The subscription period starts today. The price is set to 0.9 krona. which will provide the company with up to 36 million in total. And the proceeds will be used to commercialize the company, build the pipeline for the coming years, convert the pipeline to sales, identify additional use cases. So the commercialization is the first important part of this. The second is the industrialization, which also includes the parts production, the defense and medtech qualification ongoing, and to prove the machine in production environment. We have already communicated that the 3 largest shareholders, management, and the board intend to subscribe in the share issue. So we're confident that the outcome is going to be good.
Excellent. Thanks, Martin. So let me bring this back to where we started and highlight 3 things to remember from this session, hopefully more, but at least these 3 things. I mean, first, we are scaling parts production. Tungsten volumes for fusion and big science, like Per showed before, is happening now, not in 5 years now. 2, we are converting the pipeline. Our aim is, of course, that the proof of concepts now, both with Saab, with our orthopedic OEMs, are progressing towards, in cases of multi-machine orders and also recurring revenue as well. 3, we are now in the chapter 3 also unlocking 41 to 51 billion euro addressable market. So this comes by not just selling machines, but also selling qualified parts as well. So finally, I'm really thrilled about what chapter 3 will bring. And of course, I would love to have you with us and supporting us during this chapter as well. So with that said, thanks for your attention. And let's open up for questions.
Yes, thank you very much, Daniel, and also thank you, Martin, Per, and Göran. Göran, I'll have some questions specifically for you as well. But before we do that, I would also like to remind the viewers that to continue to ask questions in the live chat. Daniel, I think I'll finish off where the slides ended to your subscriptions. At full subscriptions, Freemelt will receive 36 million SEK before issuing costs, and the subscription period, as you mentioned, begins today. From the company internally, will you all subscribe to your share of these the rights?
So I can jump in and respond to this one. So as I mentioned, we have intent from the management team, we have intent from the board, we have intent to describe from the 3 largest shareholders. We have a number of colleagues who are also shareholders, but we haven't done the exercise to ask each and every one. But I'm pretty confident most of them or all of them will subscribe. But we haven't asked specifically.
Mm. You mentioned that you will increase focus on part production. Won't you compete with your machine customers?
But I think that's also, of course, I mean, we've been careful as well in this hybrid, let's say, approach. I mean, I think Göran also described it well. I mean, some of the industries has already started to adopt to additive, which means also started to design for additive manufacturing as well, like our medtech clients. For them, we don't need to, educate them. We don't need to push them to understand the value. They have operators, they have processes, they have factories already set up, so they need Freemelt from a machine point of view. So that's how we deliver to them. If you go to industries like Per mentioned, for instance, or let's say less mature from additive, then there is pretty much no supply chain established as well, which means that we can be a part of building the supply chain, so there's not too much of competition. So that's how we really differentiate the go-to-market.
Production of the tungsten parts.
Sorry?
Where will you do the production of the tungsten parts?
Okay. So Yes, so at the start, we have our head office here in Gothenburg, where we also have machines in-house as well. So the starting phase will be here in Gothenburg, and then of course in expansion that might be also depending on the region, as we all talked about before, about the let's say resilience, supply resilience. So, but starting point will be here in Gothenburg, Sweden.
I will, before I head to Göran, I will ask some questions that came in during the broadcast. How much has Freemelt put on development and research so far?
Was that to me?
No, Göran. I'll get to you in just a moment.
Thank you.
But this is for Freemelt. How much has Freemelt put on research and development through the years?
So thank you for the question. So the company has, since inception, had investments of around 350 million krona. The vast majority of this has gone into research and development of the product suite that the company has today. So I can't give an exact number, but the overwhelming majority of this has gone into product development.
Other questions ask the following. How durable are the printers? How many items can be printed before maintenance is required on the machines?
That's also a difficult question to answer, because there are so many ifs and buts and so forth. But I mean, typically what you have, depending on the application and the material, you have then a scheduled maintenance that needs to happen. But yeah, it's very difficult to say the number of hours, etc. But these machines, I mean, in general, they are located in very nice, clean environments and with temperature control, etc. as well. So the lifetime of a machine is fairly, let's say, long in the end.
I now turn to you, Göran. From Saab's perspective, what makes metal additive manufacturing strategically interesting for the defense industry?
A couple of things, actually. As I mentioned first, security of supply, and what we talk about in defense these days is combat mass, and that is to produce higher volumes at lower cost. And that means we cannot produce the way we produce today. We need to automate, and I see additive as a first step towards automation. We build a part in a machine. And if one machine is not enough, you can put another one next to it, and then another one, and it scales very good. So security of supply is one driver. But also, if you take a look at the Saab product portfolio, we build very complex products with sometimes pretty exotic alloys, and our volumes are not that big. At least they used to be low volume products, and for that, additive is great. And additive, with its greater design space, also allows for us to optimize for functionality in a way that we haven't been able to before. That's some of the reasons.
And with the collaboration with Freemelt, where are you today?
We have, as Daniel pointed out in the beginning, we have had a research program together on oxygen-free copper, which from our perspective is interesting. If we can print copper parts fast, it can reduce our research and development cycles. We get faster in developing and arrive at the final design for a specific part. And then after that research project, we continue our collaboration on the same alloy, the copper. And around the corner, we have some possible tungsten applications that are interesting to pursue.
Göran, there are two questions in the chat. The first one asks you the following. Are all the examples given from Saab made with Freemelts machines?
No, these are taken from history, and no, the short answer is no, but we have used the same technology when Freemelt was not around, The first example 12 years ago with the Carl Gustaf Venturi, but also the missile fin was printed with electron beam melting powder bed fusion.
The other question asks the following. You mentioned that you are typically sourcing components. What would it take for Freemelt to qualify as a contract manufacturing partner?
That we can see a good business case. It's not harder than that. I mean, we don't have machines in-house at Saab. We have polymer machines, a lot of them, but no metal machines. For metal, we rely on the supply chain. So I see a possibility for Freemelt to become one selected supplier in our approved suppliers list.
And I move back now to Freemelt, as we have another viewer question here. Which categories of defense components do you expect to experience the highest demand growth over the next 3 to 5 years?
Sorry, can you repeat that?
Which categories of defense components do you expect to experience the highest demand growth over the next 3 to 5 years?
Of course, I mean, it really comes to the point that we need to succeed in those different application development projects that we are running. But as I mentioned before, it's components within type of hypersonic missiles, in munitions, or really high heat resistance type of applications.
Another question, what type of tungsten components in the ordnance industry are best suited for 3D printing, and could you give us the reasons why?
I think, Per, maybe you can answer that.
Absolutely. Which part? I mean, tungsten is really used, as Daniel says, it has a high density, so you find it sort of in penetrators. You can find it also in maybe shape shot liners, etc. But you will also find it where you have solid rocket propellants. If you have like some sort of weapon that has to be stored for years and years, then you cannot have a cooling in the rocket engine, so to say. So therefore, you will need high temperature materials. So I would say in the top part of a hypersonics or the base part of it.
Per, I think I'll continue with you. You mentioned that the tile production demand is now and that ITER is in need of 1.5 million tiles. When does that convert?
It's a very good question, because if you mention the numbers, people think it's a long time ahead. But we talked about these 60 blankets being built right now. That is happening now. First stage now is qualify bonding methods. The second stage is to do the heat testing. The third step is to test the blankets, and that is happening now. In the next, I would say, 2 years, you do all of this, so that is happening now. What we didn't mention is that there will be a temporary wall which will be built in 2032. That will also be in tungsten, and that's also have discussions. And finally, I would like to emphasize, ITER is not the only place where we act. It is not the only place where we find fusion power plants. The quickest traction we'll find in commercial companies, and they look to ITER, they look to UKA, but which technology has been developed. So we shouldn't forget everything that is happening in parallel.
Could you give us a little bit of a description on the competition or competitive landscape in fusion tiles production?
It all comes down to what quality is needed, because there are quite a lot and high requirements on it. And what I see so far, electron beam melting is superior to many applications, and it's also cost competitive. But that will translate that also our competitors will be interested and want to move into this market. And we cannot expect that we get 100%. Markets doesn't look like that. We will have competition. But what we do much better than competition is to handle low-cost powder. We can use powder which is much less expensive than the competition.
I read now from the chat. Do you know if the two companies that won the contracting of the tungsten tiles started their production, or are they planning on how to do it? Is there a chance that they will use you as a contractor?
I would say yes to all of us. The parts has already been, first walls have been produced, they have been qualified, but they have not fitted it with tungsten yet, because that decision waits. But I cannot go into more details where we are right now. But of course we know them, and of course they know what we do. And I think I'm not going to say more.
There's another question on fusion energy. What is the time frame for delivering the first 60 volt to ITER? Is your project with the UK AEA coordinated with the F4E and ITER? If so, how?
I would say the opposite. Since the UK left the European Union, they do not work together. But sometimes they speak through us, and of course they share information. But there are no direct cooperation. But all of them, everyone in the future community would love it to happen.
If the ULI partnership develops according to plan, how significantly could the Chinese market become for Freemelts revenue within the next 5 years?
I mean, I can answer that. So, as we mentioned before as well, I mean, we did a thorough, let's say, assessment before we entered into the Chinese market. And I mean, the Chinese market is the fastest growing from adopting to additive manufacturing as well. So, that was let's say, the decision why we entered there, and also to find the right partner. And GULI, I think, is really an impressive partner. They're not a typical reseller of additive equipment. They are a leading global company, especially in energy components. So I think if you look into typically Chinese, when they invest for something, they invest for long term, and they also do the homework pretty good prior. So yes, I would say the Chinese market as such is huge. And I think with that said, of course, I mean, it hopefully becomes a really a big success also from a Freemelt perspective.
Then I believe we have the last question here. How far have you come in the 12 to 18 months time frame of the certification implant process?
As I tried to explain, when it comes to the certification part, Freemelt is not a part of that. So that is completely in the hands of the orthopedic OEMs. So at this moment now, we are in the proof of concept that one started end of 2024 and then one in mid 2025. So that's where we are.
Thank you very much, Daniel Gidlund, Freemelt, and of course, Göran Backlund.
Thank you all.